All right, my lovely viewers. Welcome to Frank Teaches MLOps. Yes, guys, yes. So today, guys, today we will be looking at something very, very interesting, right? We will be looking at something very interesting, and that is classification of machine learning, right? Would I say classification in machine learning? Thank you. Classification in machine learning. All right. You understand where I'm coming from. Just give me some time, right? Give me some time. So let me keep this by the side. So this is our topic, guys. Classification in machine learning. So I want to use one stone to kill two birds, all right? So ever since I started um um my machine learning theories, all right, I've not done much into machine learning, all right, machine learning as a topic, all right. However, sometime around 2023, I did something about MLOps, right. I would say for the first time I talked about MLOps. That was, yes, ML and MLOps. Guys, if you've not watched this video, please go and watch this video. It's over 2 years, guys. 2 years I did this. ML and MLOps. All right. So great. So great. However, in 2025, we are doing something afresh, right? We are doing something anew. Okay. So I'm going to get started from the basics. The basic, I'll be looking at what is machine learning, right? So, like I said, you have to box this, keep it somewhere, right? We are coming there. That's our topic for the day, right? But before we get here, let's first of all talk about what is machine learning, right? So, as we all know, machine learning is a field in artificial intelligence, right? So, ML, I'll be abbreviating it as ML, is a field, right, in AI, right? It's a field in AI that that focuses on what, on developing algorithms, that focuses in developing algorithms, all right, that that machines that systems uses to learn from what, from data, without what, being explicitly programmed. Yeah. All right. So there are n number of definitions out there about machine learning. You can just say machine learning is a field of AI, all right, that learns from data, right? That has the autonomy to learn from data. So there are a lot of different definitions out there depending on the author, but all of those definitions, they are pointing to the same thing, meaning that, right, you have a system in place, right, that's just on its own, based on different algorithms that it has, all right. Based on those algorithms, it's and if based on those algorithms, and if those algorithms have been fed with data, it takes the data, learn from the data, and make predictions out of those data without much of programming. All right, great, guys. So that is what machine learning. So this now brings us to the next topic: types of what, machine learning. Types of what, machine learning. All right. Unarguably, there are different types of machine learning. We have supervised learning, supervised learning, and we have unsupervised learning, unsupervised learning, and there's one other learning, very autonomous. We have what? Reinforcement learning. Now we're going to see this learning bit by bit, right? Bit by bit. Okay. Now, what's unsupervised learning? So it's sorry, what's a supervised learning? A supervised learning is a kind of in a layman way, as the word implies, supervised. It means that there is a defined input as against what the output would be. Now, there is an input already. There's a defined input, is defined, right? This input is fed into a what? A machine learning model. A model is the algorithm, right? It's fed into a model, and you have a what? An output already. What it means is that from the very beginning, you know what the output would be. From the very beginning, you already know what the output, all right, will look like. Now, for instance, all right, I have a truck. This is my object, and it's labeled truck. All right, it's labeled a truck. Now, I impute this into a what? Into a model. The model should predict what object is this. You definitely give me a truck. From the beginning, I know what all the outputs will already be. So in contrast, we would say that, let me clean this. So in contrast, we would say a supervised learning, right? A supervised learning, right, is a form of machine learning, all right? It is a form of machine learning that uses labels, all right? That uses labeled data sets, right? Right? To train a model, to train a what? A model. It uses labeled data sets, which I just illustrated, right? A labeled data set, you now you have a truck. Let's go to Google. Google truck images. Let me use this. Let's copy this image. This happens to be my data set. This is an object, and this object is already what? It's already labeled. Let me use green. In machine learning, most times green is used to label a data set. And this is truck. So we've already what labeled this of these data sets, the data sets. And if you feed this guy into a model, this is your model. All right. So the model will learn, it will automatically learn that this is a truck. And it will output, it will make a prediction that yes, that is actually what? A truck. So that is what a supervised learning is. It's a form of machine learning that uses labeled datasets to train a model, a labeled dataset. So based on this labeled dataset, you're going to use that labeled dataset to train what? To train the model. So let me keep this somewhere. Let's keep this somewhere. So yeah, good. Now, in unsupervised learning, so unsupervised learning, right? It is a what? A form of ML, right? That learns from patterns. It learns from patterns, okay? From unlabeled data sets. So the form of ML that learns from what? Patterns, structures of unlabeled data sets, all right? Without any guidance, without any guidance. Now, an unsupervised, as name implies, it's it learns from unlabeled data sets that are not identified, data sets that are not already labeled, data sets that are raw data sets, raw data. Nothing has been done to the data sets, to the data. So with unsupervised learning, it's an unsupervised learning, right? The model goes into you feed the model with data, right? Based on the patterns, based on the patterns already in data, the model will learn automatically. It will learn on its own, right? And make what? Reasonable predictions. To make reasonable predictions. So an unsupervised learning is a kind of an unguided learning. Unguided. There's no guidance because the data are not labeled, right? So I would say that unsupervised is an unguided form of ML, right? It is an unguided what? Form of what? Of ML. Great, great. The last but not the least is reinforcement learning. So in reinforcement learning is a special kind of learning, all right, where machines learn to make decisions on their own, right? It's a form of ML where machines, right, learn to take actions, make decisions, right, on on their own, on their own. That's reinforcement learning, all right? It's a kind of trial and error form of learning, all right? So can go further. It is a form of trial and error form of learning. Okay, it's a form of trial and error learning process. Okay, learning process. Okay, where machines, you know, where machines, where machines explores environments, right? Explores environments. Based on that, they take actions. They take actions, right? And they receive feedback. They take actions, and in turn, they take actions, and in turn, receive feedback, right? They receive feedback in the form of a reward or a penalty, in the form of a reward or a what? Penalty. So this is what a kind of reinforcement learning is all about, right? So this feedback at times it helps the machines um to learn on which actions are most effective, you know, in achieving their goals. All right. So you can see these are the different types of machine learning. All right. That being said, guys, that being said, let's now quickly look at machine learning life cycle. All right. Let's quickly look at machine learning life cycle. What are the processes, right? What are the processes that we need to go through, okay, in what? In developing um, um, a machine learning model, right? Or in deploying, all right, in deploying a machine learning model. Let's look at that quickly. Machine learning life cycle. All right. So in the ML life cycle, we have first, the first stage is data acquisition. Now, in acquiring data, right? Because a model is nothing except data. A model can do nothing except it's being fed with data. Data is the ultimate. It is what a model depends on. All right. Data is what a model uses, right? Based on that to make what? Predictions. So without data, there is no prediction, right? So you have to what? Find your source of data. So this defines the data source. Now, after this data has been acquired, it could be from anywhere. It could be from a live stream. It could be a data at rest, right? Right. So your source could be data in real time, data in what? Real time, right? So your source could also be data at rest, data at rest. All right. So it could be from anywhere. So this data source, right? So the next on the agenda in that flow is data cleaning. Now, before a data set is fed into a model, the data must be cleaned, right? Are there any missing records in the data? Are there columns that need to be readjusted? Are there labels that need to be kept properly? So there are a lot of, you know, data pre-processing. All right. So we could also call this data pre-processing. Data pre-processing, right? It's a form of cleaning data, making the data ready for model development. Okay, great guys. Now, after data cleaning, the data has been cleansed. All right. The next stage will be model training and development. Model training and development, right? So this is a stage. Oh, model training and development, right? So this is where you now start looking for appropriate algorithms, right, to train your model, right? So you have to the nature of your data will determine the kind of algorithm, all right, you use to what? To develop and train the model. The nature of your data, right? There are two major categories of data, right? There are continuous data, and there are object data. So continuous data are data gotten from are numbers, right? Are numeric data, right? So continuous data are numeric data, while object data are things like objects, right? Right? Animals, disease, anything objects, all right? So You have to define what's the nature of your data. Based on the nature of your data, you now know the appropriate algorithm you use to train and develop the model. All right. So that happens here. So before that happens, you need to now split this model into two sets. All right. All right. Into two sets. The first set happens to be which comes the first set happens to be the test data, the test data, and the other would be, all right, would be the model test. Now, based on the model training, all right, now you've splitted this into two parts, which is sorry, this is the next page. Please. Sorry, let me remove that phase first. Right. So now this data will be splitted, right, into a training set and a training data and a what? And a testing data. So now you have to divide your data sets such that um the training data, it could be maybe you assign 80% of the data sets as your training data, and you assign a 20% of a data set as your what? As your test data, right? So now, once this has been splitted, okay, now you now use, based on that, right? Based on that, you now develop your what? Your model, right? You develop your model. Once the model has been developed, you need to test the model to check if actually the model is making the right predictions. If actually the model is meeting with the accurate predictions, making the right call, right? So the next phase now is around what? Model testing. So you need to test your model, right? So if you use the test data, based on the test data, you input the test data into your what? Into your model to check if it matches what you use during what? During training, right? If it corresponds to, or it's close to, or if it's above, it shouldn't be more than, right? For instance, I have let's say I have a data set, right? A housing, let's say a housing, a rental, a rental data set. Now, in this rental data set, it is organized in such a way that based on the number of rooms, all right, and the square feet area, right, based on these two features, the number of rooms and square foot area, right, I need to determine the price of the apartment. Now, when you're going to look for an apartment, all right, maybe what you have in mind is I need two bedroom flats, and the square foot area should be, let's say, 50 by 50, 600 by 600, or as the case may be. Based on these values, based on these features, I want to determine, based on the features, the price will be determined, right? Based on the features, the price of the apartment, right, will be what? Will determine. So based on these two features, the price being the label, all right, price will be what? Determined. Now, This is my data set, which I've imputed. I've split this data set into two parts, a training set and a what? A testing set. All right. Based on that, I've trained my model. All right. I've developed my model. I've trained my model. I've developed the model. I've trained the model. Now it's now time to test the model, right? If what I was given, all right, is 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 a bit, it shouldn't be too far. For instance, now for a 2-bedroom flat, all right, and a square feet area of 600, the initial data, right, the price should be something around, let's say the price is something around $1,000 for this feature of a room. Now, after training my model, and I now notice that the number of rooms still two, and the square feet area, the area 600, but the price is $2,000. Then there could be something there could be an issue with my model. So based on this prediction, $2,000, the initial data I had was $1,000 based on requirements. But now, same data, same number of rooms with same number of area, my model is predicting what? $2,000. So it is, I'm looking at it as it's too much. It means it's times two of what we had initially from our data sets. So what will happen is I'll now what? I'll now fine-tune. If my data, if my model is not performing as expected, right? I will now do what we call fine-tuning. I will try to fine-tune my parameters, which is known as parameter tuning. So I'll retrain the model. All right. I'll try to fine-tune. So this aspect we call parameter tuning. Right? Parameter tuning, right? So I will retrain the model. And once I retrain the model, it goes through the same process to back to model test. I will test the model. If it now falls in line, then I will now prepare for what? Model deployment. So that will be the last phase. All right. So this aspect will now be model deployment. So some authors call this stage as model evaluation. You're evaluating the model, right? You could also say model evaluation. Model evaluation. Model evaluation. So this stage, you're also what? Testing, evaluating, right? Checking the outcomes, right? What have been given. Okay. So if everything goes well and your model is in line, right, then you can now go ahead to deploy the model. So this is a rundown of what a machine learning life cycle is all about. All right. Great, guys. Great. So now that now brings us to the aspect that we are getting into, which is all right, classification in what? In machine learning. Now let's now look at what problems does machine learning stand to solve. What problems does machine learning solves? There are two major problems. There are two major problems that are peculiar to machine learning. Two major problems that machine learning stand to solve. The first problem is a classification problem. And the second problem is a regression problem. Now, classification problem and regression, these are two huge topics, very huge topics, right? So for today, we will be talking about classification, classification in ML. We will be talking about classification in what? In machine what? In machine learning. Maybe in our next video, all right, we shall talk about what? Regression what? Problem, right? But for today, let's look at classification problem. So now, the question now is, what is classification? Like we earlier said, earlier said there are two problems that machine learning solves. One is a classification problem, and the other is what? Regressional problem, right? Now, let me forget about regression for now, and let me face what? Classification. Maybe in our next episode, we shall talk about what? Regression what? Problem. So classification problem. What is classification in machine learning? So classification, as the name implies, all right, is a process of grouping. It is a process of, I would say, categorizing or grouping data into predefined classes or categories. When you group a data set, right, into something that is already defined, right, you're doing a classification. For example, we could class airborne diseases. Airborne diseases. So I can come here now. Can come here and list of airborne diseases. So airborne diseases is a classification. So let's look at them. Coughing, okay, is categorized respiratory symptoms and flu-like symptoms. Now, and other general symptoms. Now, airborne diseases are categorized into respiratory symptom, flu-like symptom, and general symptom. So for respiratory, we have coughing, sneezing, runny nose, sore throat, shortness of breath, difficulty breathing. That's under respiratory. Now for flu-like, we have fever, chills, fatigue, body ache, headache. And for general symptom, we have watery eyes, chest discomfort, wheezing, rapid heartbeat, nausea or vomiting in some cases. So you can see how we have been able to classify airborne diseases. So if I'm to solve a problem, if I'm to develop a model that solves a problem in the healthcare or within airborne diseases, all right, then the kind of problem I'll be solving is a what? Is a classification problem. It's a classification problem. And for classification problem, there are specific algorithms that I need to use to solve such a problem. We are going to get there. All right, we are going to get there. Okay, so going further, we could also say, all right, we could also say that um we could also say classification. We've already said it. All right, grouping your data sets, all right, into different categories. Now classification has types. This is what classification is all about. Now, types of classification. Now, classification has what? Has types. There are four major types of classification. Four major. We have the binary classification. We have the multi-class classification. We have multi-label classification. And finally, we have the imbalanced classification. Now, let's start by defining and giving examples of each of these classification types. So now, for the case of a binary classification, right? Now, first thing first, you have to determine the type of problem you are about to solve, the type of machine learning problem you're about to solve. Now, you've determined that this problem falls in the category of classification. It's a classification problem. Now that you've defined, you've identified that it's a classification problem. The next approach will be what kind of classification? What type of classification? Is it a binary classification? Is it a multi-class classification? Is it a multi-label classification or an imbalanced classification? That we are going to see in our next flow. So binary classification involves all right, predicting between two classes. This involves making predictions between two classes. For example, all right, I'll give an example somewhere. Okay, let me copy this out. All right. Binary classification. Right. So this involves making predictions between two classes. For example, you have, let's bring back our truck. You have this truck. Oh shit. For example, you have the truck. You have truck, and then let me also look out for dog. Can I have a PNG? Oh, I can't have a PNG. All right, let me copy this. Copy. All right. Now, it's a prediction between two classes. So this is a truck, and this is a what? It's a dog, right? Now, if I impute, this is already labeled. Remember, classification problem falls in the category of a supervised learning. A supervised learning, what did we say supervised learning is? Supervised learning is a form of learning, right? That uses what? Labeled data sets, right? You feed in a labeled data set into a model, right? Now we have a model. You have a model. This data set is a labeled data set, which is a dog, right? It's already labeled. When you feed this information, this data set into this model over time, right, is going to learn that whenever you see an object like this, it's a dog. All right, it's a dog. It knows that this is now a dog. It will learn it because it's labeled. Based on that label, it has identified it as a what? As a dog. Now, once you feed this guy as an input, as an input, as an input into this model. All right, this model makes predictions based on what it has learned. It will now output the information and to tell you that what this is a dog. It will output it and tell you that the object that you fed into that model, all right, that object is what? It's a dog. So this is a binary classification. It's either a dog or not a dog. It's either a dog or not a dog. All right. For instance, now, in the context of emailing, all right. Okay, let me say example. So, e.g., of a typical example of binary classification is you are making prediction. You want to make prediction using two class. It's either A or not A, right? It's in the context of emailing. You know, in email, we have what we call spam messages. It's either the message sent is a spam messages, the spam message, or it is not a spam message. All right. So similarly, the next could be is either a dog or not a dog. So once you see such a problem, you know that this problem is categorized as a binary classification. Now, similarly, it's either a patient in clinical, in medicals, it's either a patient has a disease or the patient does not have a disease. All right. So this is what binary classification stands for. All right. Now going further, we have other ones like multi what is that one? Multi-class. All right. So in multi-class, multi-class classification. So in multi-class, all right. So in this multi-class, it involves predicting. This involves. I should have. Let me just copy this at once. So multi-class, right? Multi-class classification. This involves making predictions between more than two classes, right? Between more than two classes, okay? More than two classes, okay? Now, for instance, sorry, for instance, copy. I have a truck. I have a dog. Let me look for a cat. Then I have a cat. So in multi-class, we have a truck, we have dog, and we have a cat. So this is multi-class. So it's more than what? Two class, right? More than two class. Okay. So Based on what I have, right, I will feed this to my model, right? I'll feed this to my model. And to make the predictions and tell me that that is what? The cat. So in here, I have more than one. In here, I had just a dog. I have in here, I have more than what? Two classes or more than one classes, as the case may be, right? So that is a multi-class classification. And in multi-class classification, there are n number of algorithms, right? We could use, all right, to train the model, right? However, today's class is not today's session is not about machine learning algorithm, right? Maybe I'll come up with a different series that talk about what? Machine learning algorithm. All right. Yeah. So moving forward, we have multi-label, right? Multi-label kind of classification. Let's check this out. All right. So multi-label. So multi-label classification, this involves, all right, predicting mono this involves making predictions or predicting more classes for, okay, this involves um predicting more classes, right, for each input label. Now, what this means is that in a multi-label, all right, in a multi-label, let me copy all of this. See, paste. In multi-label, let me add one more object. I can say bird. All right, copy. So in multi-label, all of these are seen as a what? As a single object. All of these are identified as a what? Single object. Let me draw triangle around it. Okay, sorry. All of these is identified as a what? As a single object. So I'm going to feed this into what? Into my model. And based on what the model I've based on what has been fed into the model is going to be trained based on this object, and it's going to what? Give an output. It's going to tell us that in that object, in this image, it's going to identify the object in this image. So inversely, this is an image. All right. In this image, there are objects. Okay. So in this image, the model is able to identify that there's a dog in that image. There's a dog. It also identifies that there is a truck. It also went further to let us know that there's a what? There's a cat. And finally, it came up and said what? There's a what? There's a bird. So this is a multi-label classification. Now, this is the application of this kind of problem is seen in computer vision. Now, in computer vision, what happens in computer vision is you have a stream of video, right? A stream of video, and in that video, right, you can automatically identify objects in the video by labeling them. You could identify human being. You can identify different objects. You can identify if that human object is carrying a knife or is carrying a gun or whatever. The same thing is applicable when you feed an image. This is an image. Here's an image. When you feed this image into this model will study the pattern, learn from that image, and try to what? Identify the objects in the image. Such class of classification is known as what? Multi-label classification. So those are everything about that. Now, the last but not the least is imbalance. All right, imbalance classification. Imbalance. So imbalance classification. So in the context of imbalance classification, right? We would say that this involves unevenly. This involves unevenly distributed, right? Unevenly distributed classes of objects. Classes of what? Of objects. When objects are unevenly distributed, we could term such a data set, right? When a data set is in a data set, you have a data set. In that data set, you have different categories of data, right? And when the categories of data are unevenly distributed, all right, it will fall in the category of imbalance classification. And imbalance classification has its own problem. For example, now you have a data set. Let's say, for example, I have, let's say, okay, for example, let me remove this. For example, all right, I have three class of classification scenarios. All right. Where my training data, or I would say where my data sets, all right, data set contains the following: 60% of truck, 25%, right, of, I would say, of plane, and 15% of dogs, planes, trucks. All right, 60% of trucks, 25% of plane, and 15% of trucks. Such a data set will automatically fall in a category of what? Imbalance. Imbalance in the sense that you have more trucks than plane, and you have more plane than dogs. Now, what this goes to say that there's a probability that if I feed this data set into a model, there's a probability that the machine learning model can never learn that there's a dog in that data set, right? So it will be producing more of trucks. It will be predicting more of trucks, thereby making the system bias or making the model bias. So in this kind of scenario, there's a huge problem again. There's a second level of problem. First, we are trying to solve a classification problem. Now, secondly, we are also trying to solve an imbalanced problem where we have an imbalanced data set. Okay, so you can see there's a problem here. So this model will always be biased. All right, will always what? Be biased. Okay, great. So it now goes to say that we can't use conventional conventional predictive models, right? Such as or conventional predictive algorithms, right? There are different kinds of algorithms, which, like I promise, I will teach in our next series. All right. So there are different algorithms. There is logistics regression, decision tree, k-nearest neighbor, clustering, gradient boost, etc., etc. Right? However, we can't use those conventional algorithms to solve such a problem, because if we try to do that, the system will be biased, such that it will, at every instant, always predict that the object is a truck, because we have more trucks. To solve this problem of imbalanced classification, there are two major methods we could employ to solve the problem of what? Imbalanced classification. Solving imbalanced classification problem. The first is what we known as sampling technique. Now, in the context of sampling technique, all right, we are going to apply some techniques, right? The first technique which I look at is random undersampling. Now, what we will do in this context is, now, since we have a majority of we have 60% of the truck, right? We are going to randomly eliminate, all right, from the majority class. So truck has majority class, and the second majority class is in plane. Plane has second majority class. So for the method of random undersampling, right, we're going to randomly eliminate what? From the what? From the majority class, which in this context happens to be what? Trucks. So we're going to reduce some data, some of the truck data sets, right? Reduce it such that it tries to match up with planes and dogs. All right. So we're going to increase the second sampling method. The second method is random, or what we call smooth oversampling. Smooth what? Oversampling. So in here, we're going to randomly what? Replicate. All right. Randomly what? Replicate from the what? Minority what? Minority class, which happens to be what? Which happens to be dogs. So either method we could use for our sampling technique, either one that you want to go with. You must not go with the two. For either method, either you are eliminating by reducing it from the majority class, or you are increasing from what? From the minority class. So with these methods, all right, with this method, you can comfortably, all right, solve the issue of what? Imbalance what? Classification. All right, can solve the problem of what? Imbalance classification. All right, great, guys. Now, the last but not the least, in the context of classification problem, like I earlier said, classification is a very broad topic, very, very broad topic. So I'm just trying to, you know, I'm just trying to fit in every aspect of classification in machine learning into one simple, all right, track. All right. The last aspect is metrics to evaluate machine learning classification algorithms. What are the metrics? Metrics to evaluate machine learning what? Classification what? Algorithms. Algorithms. There are different metrics, right? The first metric is accuracy. Accuracy. The second metric is precision. Precision. Third metric is recall. The last but not the least is F1 score. So these are different metrics we could use to evaluate, right, the performance of a what? Of a machine learning classification what? Algorithm. Okay? Algorithm. Great, guys. Great. We are getting there. All right. Great. We have accuracy, we have precision, recall, F1 score. All right. Great. So going forward, we can't really talk about metrics for evaluating machine learning classification without, most importantly, mentioning a technique used for evaluating the performance of the metrics. And such technique is known as confusion metrics. All right. So this is a caveat. Note, we might not, or I would say, our illustration of classification in machine learning will not be complete without mentioning a technique used for evaluating the performance of classification metrics. Classification metrics. Our illustration of classification metrics in machine learning will not be complete without mentioning a technique used for evaluating the performance of these metrics. And such technique is known as confusion metrics. Confusion metrics. Confusion metrics. So by definition, so what it means that, so with confusion metrics, we can easily evaluate the performance of these metrics: accuracy, precision, recall, F1 score. Now, what is confusion metrics? Let's look at that quickly. I think this is the last part. Confusion metrics. What is it? Confusion metrics. So by definition, a confusion matrix, right, we would say a confusion matrix is a simple table. It's a table that summarizes, right, The table that summarizes the performance, the what? Performance of classification what? Models. Classification what? Model, right? Classification model by showing counts, of true positive, comma, true negative, comma, false positive, and false negative. I take that again. A confusion matrix is a table that summarizes the performance of your classification model by showing the counts of true positive, true negative, false positive, and false negative. This is what a confusion matrix is. Actually, I was even confused the first time I heard of the word for the first time, confusion matrix. I tried to understand, try to wrap my head around it, but it didn't make sense. But at some point, it started sinking and started making sense. All right. So I'll try as much as possible to explain what a confusion matrix is. So the bottom line is a confusion matrix is used, all right, to analyze the performance of classification model. How is your model performing? Based on confusion metrics, you get to realize how are these guys accuracy, how is it performing? Precision, how is it performing? Recall, how is it performing? F1 score, how is it performing? So confusion metrics will help us to achieve that. All right. Now, before we go into designing uh, our table, our table, which is the confusion metrics, let's take a context. For instance, imagine you are in a healthcare. All right. Let's take a case study. Case study. Case study. Assuming you are a health care provider, all right, and you want an AI assistance, all right, an AI assistance um to predict where patients, all right, where patients where a patient has a heart disease or or does not have a heart disease. You already know what problem is this. What kind of classification is this? All right. Such a classification type that involves predicting a yes or a not, a yes or a no, a positive or a negative, a 0 or a 1. Such is a binary word classification. And to solve this problem, it's a problem of what we use what binary classification to tackle this problem. Right? So we are assuming, here's our case study. We are assuming that you are a healthcare provider and you want an AI assistant to predict. You want an AI assistance to predict where a patient has a disease, whether a patient has a disease or does not have a heart disease, whether a patient has a heart disease or does not have or does not have a heart disease based on its based on its health record, right? Based on his record, right? So this kind of problem um is already a binary words, classification. So based on this information, right, let's now draw our confusion matrix. Okay, so confusion matrix is easy to draw. Okay, very easy. Let's do something like I don't know how I'm going to get this. Let me draw table. Okay, dynamic table. Okay, okay. So let me add. Okay, um um let me add. Can I remove? Wow. I'm trying to design. Okay, let me use lines to design this thing. Let me use lines, guys. Let me use lines. Let me use lines. Wow. Okay, let me use lines to design this. All right. So I have something like this. Okay. And I have the next one. Great. Okay. So still come back here, vertical. I have something like this. Okay. All right. So okay. Let me okay. So great. Based on that, all right. So let me be putting I have this already. I think I'm doing pretty well. Okay. So let me put my text. So I have my predicted condition. Condition. I can show you a sample of a confusion matrix. Let's look at confusion matrix. Right now, let's look at the definition one more time. It says what confusion matrix is a table that summarizes the performance of a classification model by showing a count of true positive, true negative, false positive, and false negatives. Right? It is a fundamental tool in machine learning for evaluating how well a model distinguishes between what different classes. Right? So I go to images, I'm going to see a whole lot of what confusion metrics. Right? This is what I want to design. This is what I want to design. Okay. This is what I want to what design. So I'll have my predicted condition and my actual condition or my true condition. So let me copy this guy, copy this image. Come over here, right? So let's place it somewhere here. Okay, that's too big. Great. All right. So based on this now, I'll come here. So here is my predicted condition, right? So in my predicted condition, I have I'll divide, yes, I'll divide control C that. So I'll have what? I'll have positive or predicted positive, and predicted positive, right? I will have predicted positive. Let me reduce this a bit. And predicted negative. Great, right? So based on that, I'm going to have So under copy and paste, no, sorry. So based on this info, right, I'm going to have true positive, that's TP, and true negative. True negative, which is TN, then I'll have false negative, FN. I'll have false negative, and I'll have false positive. False positive. You can see we have this column, all right? Predicted positive, we have true positive, false negative, predicted negative, false negative, true negative, right? You can true positive, false. All right, it's the same line. You can see false positive, false positive, which is positive test, predicted positive. All right. Then finally, we'll extend this guy. We're going to extend U, right? We're going to extend U. Okay. We'll call that our total observation. We're going to say our observation. Observation. So here's our observation with total observation, right? So I need this. Our observation is that, okay, then I'll extend this and this. I'll extend that. Good. All right. So what we have is condition positive. All right. And condition negative. Condition positive and condition negative. So in condition negative, we have all negative or have negative, right? All right. So you can see here, test negative, test positive. All right. Great. Then finally, we have this. Finally, we have this. We now have our what? Our true condition. True condition. So in true condition, we have condition positive, condition negative, right? So based on this, this is a typical representation of what we known as what a confusion what matrix, right? A confusion matrix. Based on this, we can now go ahead, right, to compute what our value of accuracy will be, our value of precision will be, and recall, and finally what? F1 score. Now let's come back to our case study. Our case study says something. Assuming that you are a healthcare provider and you want an AI assistant to predict whether a patient has a heart disease or does not have a heart disease based on its what health record. Now let's look at this now. True positive says that, all right, the patient, your true positive means the patient has a heart disease and the model predicted positive. Now let's do this. It's just logical, guys. So TP means the patient has a what? A heart disease. And the model predicted positive. Predicted positive. That's what? True what? True positive. True negative. The patient has a heart disease. But the model predicted positive. The patient has a heart disease, confirmed and true. But the model predicted negative. It is confirmed that yes, the patient has what? A heart disease. But the model predicted what? Negative. False positive. The patient does not have a heart disease. The patient do not have a heart disease. However, but the model predicted that there's a heart problem. Positive. Then finally, false negative. The patient do not have does not have or do not the patient do not have does not have a heart disease, does not have a heart disease, and the model but the model predicted negative, and the model predicted what? Predicted negative. So this is the rundown of what? The confusion metrics. And based on these outputs, you can now what? Start determining what accuracy will be. What your accuracy will be. Your accuracy based on what we have before us in our confusion metrics. So accuracy will be true positive plus, all right, true negative divide by total number of what? Observations. So your total number of observations, you must have it, right? Total number of observations. That's accuracy. Now, what precision would look like? Precision. So precision will be what? True positive divide by divide by 1. True positive plus false what? Positive. Similarly, your recall will be true positive divide by true positive plus false negative. And the last but not the least, your F1 score will be true, will be 2 multiplied by precision times your recall divide by precision plus recall. So this way, you can see how we've been able to what? To use what? Our confusion metrics to determine the performance of our what? Classification, to determine the performance of our classification was model, right? So far so good, guys. This is everything about classification in what? In machine learning. We started off with looking at what machine learning is. We went further to talk about types of machine learning, which is categorized as supervised, unsupervised, and reinforcement learning. So we are meant to know, understand that supervised learning makes use of what? Some labeled data, right? Labeled data, while unsupervised does not use what? Labeled data. And reinforcement learning is a type of learning that learns on its own. The system on its own with no guidance, all right, based on patterns and structure, it learns from a given what? Data set, right? And it's a type of it's a kind of a trial and error learning process where the system, right, when it performs some actions correctly, is being what? Is being rewarded. But if it performs some actions wrongly, it will what? It will be penalized. Such is categorized as a reinforcement what? Learning. We went further to look at machine learning life cycle, where we talk about the different stages, right from when the data is being acquired to when data is clean to when that data is being used for training, and when the training becomes a model and the model gets deployed, right? So those are machine learning process. That now brings us to what problem does machine learning actually solve? We are meant to understand that machine learning solves two problems. One is a classification problem, and the other is a regression what? Problem. And we saw what classification is. A regression, we were told that regression is a kind of a continuous or a continuous values, right? Continuous value we are is termed as numbers, numeric values. That's what regression stands to what? To solve. Now, in context of classification, there are different types of classification. There's a binary classification, multi-class, multi-label, and imbalance classification. And we all saw the different definitions and their examples of these classification types. And we went further to look at the metrics. How can we evaluate the classification algorithms? And we looked at what? Accuracy, precision, recall, and F1 score. And finally, an important technique which must be mentioned, which is used, all right, to summarize the performance of the matrix of classification what? Model. And that technique is what we know as what? Confusion what? Matrix. To further buttress on how to apply confusion metrics to evaluating the performance of classification model, we painted a scenario, a case study, where a healthcare provider uses an AI assistant to predict whether patients have heart diseases or they do not have heart diseases. So based on the case study, we were able to what? To set up a what? A confusion metrics table. So in the confusion metrics table, this was our outcome. And based on this outcome, we now use this to compute the metrics, the classification what? Metrics, like accuracy, precision, recall, and F1 score. That being said, guys, I hope this session has been very, very informative. And I hope to see you guys in our next episode. Our next episode will be on regression. After regression, we'll move into what? Machine learning algorithms. Thank you and see you in our next series. Peace out.